welcome Annalisa Pillepich from the Max Planck Institute for Astronomy, who will be talking about how to form galaxies and stars and the cosmological web on a computer. She will be speaking about the IllustrisTNG simulations and the physics and science that we can deduce from these simulations. Welcome also to Albert Einstein, who is our silent guest for today, another guest of honor. And I don't need to introduce him, but I would like to introduce Annalisa. She did her PhD in Zurich at the ETH. From that, she was a postdoctoral fellow at the University of California in Santa Cruz. From that, she moved on to the other coast of the United States, to the Harvard-Smithsonian Center for Astrophysics, where she stayed until, from October 2013 to June 2000, or to May 2016, and it's her one-year birthday, being in Heidelberg as a junior research group leader at the Max Planck Institute up the hill. So welcome also to the latecomers. And let us, of course, welcome Annalisa for her talk.
Thank you very much. Good afternoon. It's a great pleasure to be here to introduce you all to IllustrisTNG. TNG stands for the next generation, and as the name is meant to evoke, IllustrisTNG builds upon the scientific successes of its predecessor, the Illustris simulation. You can see this Illustris simulation depicted in the movie that was going on for a few minutes before. This is a movie made by my colleague Mark Focusberger a few years ago. Illustris was one of the first large-scale cosmological simulations which was capable of returning quite a diverse galaxy population, yet with a fixed set of physical recipes. In fact, Illustris could follow the evolution of thousands of galaxies from high redshift to today, and here you could see a subsample of the box. At the beginning, you could see the dark matter density, then the movie turned into gas density, gas temperature, gas metallicity, and all this to highlight the interplay between dark matter, gas, and galaxies, and the feedback that the galaxies might exert into the surrounding medium. This is, for example, is clearly seen in these bubbles of energy thermal dumps, and these were the AGN feedback which were implemented in this model. So this slide is my personal and special thank and acknowledgement to the work of the people that have done Illustris in a time when I didn't even work on these kind of topics. So it's fine. Just what are we going to talk about? So as you can imagine, the topic of the talk is going to be about cosmological gravity, magnetohydrodynamic simulations for galaxy physics. I will actually try to give an account of the works which have been done with the repo after Illustris, but actually I will focus only on those efforts aimed to make large-scale cosmological volumes. So I will not mention all the other cool research lines which are undertaken here in Heidelberg with the CODA repo itself. I will take a bit of an historical note. I will review Illustris, its achievement and the limitations, because I want to tell you why we went to do the IllustrisTNG project. And then I will indulge quite a bit in details of the underlying physics model, on details of the feedback in the way we implement them. And this is not because I want to bore you to death, but it's rather because I want to give you tools to understand on your own the strengths and weaknesses of this type of numerical experiments. And of course, then I will show you how we use these simulations, and I will range from galaxy colors to the mass assembly of the most massive clusters in the universe to the effects of baryons on the underlying dark matter. And before starting, it goes without saying that today I'm actually acting as a spokesperson for a group of people. This is the IllustrisTNG team. It's a bunch of guys, mostly between Heidelberg, Munich, Boston, and New York, all captained by Volker and Lars Enquist. All right, so let's start from Illustris. If you have to imagine the Illustris simulation, you want to put it in the same bucket of other type of simulation that you might have heard about, Eagle, Magneticum, Horizon AGN. These are all simulations for galaxy physics, so with baryonic processes, on cosmological volumes. So all these type of simulations could follow thousands of galaxies on something like 100 megaparsec side volumes, with what you could, if you have to remember a few numbers, with a spatial resolution of the order of the kiloparsec, of half a kiloparsec, with the stars representing stellar population of about 10 to the 6 solar masses. So of course, these simulations are not competitive with respect to those which actually are focusing all the computing power in one only object. These are called zoom simulation, similar type of physics of these large volumes, also cosmological initial conditions, but just one object, or two, or a few, and of course they can push the resolution to much, much higher limit. At the other end of the spectrum, on the other hand, there are of course the large, gigantic, gigaparsec scale, n-body only, or gravity only, or dark matter only simulations. And to give you the historical perspective, if Illustris and Eagle came out something like 3 or 4 years ago, they came out 10 years after the biggest, well, the coolest, because the millennium was 2005, simulations of n-body type. All right, so why can't we do simulations like this on these gigantic gigaparsec-like volumes? Because we want to model galaxies, and of course, the physics of galaxies is much more complicated than the hierarchical growth of structure and the gravity interaction that characterize the n-body only, dark matter only simulations. And I'm sure I don't have to convince this audience that galaxies are complicated objects. They are not just simply an ensemble of stars in the middle of a dark matter halo, which we can put it here. Of course, we know there are stars formed out of pockets of gas, very dense, molecular. There are other types. The gas inside the disk of galaxies can assume very diverse properties, not just properties of the circumgalactic medium. Then we know also that stars can evolve in very complicated manners. Some end up in supernova. Some end up in black holes. In any case, observations also tell us that at the center of our galaxies, or almost all of them, there is a supermassive black hole. And these supernova and supermassive black holes are particularly important for the kind of simulations we are doing. Observations seem to suggest that they exert feedback in the surrounding, meaning there is a return of mass, of energy, or momentum from supernova or supermassive black holes. And we need to implement those. In fact, this type of feedback from stars or supermassive black holes have been shown to be one of the most pragmatical and successful way to avoid that in our simulation we overmake stars. And this is why I will talk about the feedback in quite some details. So Illustris in one slide, I told you already quite a few things. As I said, it was a 100 megaparsec side volume. If you can find a problem with this volume, is that the biggest object that you can reach in this kind of volume is of the order of 10 to the 14 solar masses, although there are thousands and thousands of galaxies. I think the greatest achievements of my colleagues when they made this Illustris is the following. They took all the physical recipes that they thought that were relevant for making galaxies. They decided on some 3 parameters based on more or less two statistical quantities, the star formation rate density as a function of time, and the stellar to halo mass relation at redshift 0. That's what they tuned the models to, and what they came out with was a galaxy population which showed naturally disks and bulges and red and blue and galaxy and so on and so forth. How did they achieve that? Behind Illustris there is the Coda repo made by Volker. Many of you are very familiar with this. Let's just put 3 keywords. It's a multi-purpose code and it's a moving mesh. When we use it to do cosmological simulations, It follows the coevolution of dark matter, gas, stars, and black holes. And dark matter, stars, and black holes are sampled like particles, but the gas is sampled like cells. So in fact, Arepo is not particularly different from other codes when it has to do with solving the gravity equation, but it's quite peculiar and cool when you have to solve the hydrodynamic equation. As I said, it is a so-called moving mesh. So the gas cells are sampled as grids. The grid cells are not fixed, they are not rigid, and they're not Euclidean. So in fact, they can assume any possible shape. And here you can see how it works, because the cells can actually move with the bulk motion of the flow over which they are solving the Riemannian equations. And therefore, you end up with very, very small cells at the very middle of your galaxy, where your density is high. But of course, you can also have very, very large cells in the intergalactic medium or in the circumgalactic medium. Okay, then of course, the code has many additional features, but even if you solve gravity, and even if you solve hydrodynamics and you have all your gas, this doesn't mean that you make necessary galaxies. In our framework, we need what is called the model, the galaxy formation, galaxy physics model. This is summarized here in a plot that actually I don't want you to read. I just want you to see that it's very complicated and that there are many things going on. Of course, I talked about the numerical method, and then, well, we have to have actual prescription on how to transform gas into stars. And then we also have recipes on following the evolution of stars and allow them to enrich the interstellar medium with heavier elements than hydrogen and helium. We also need laws on how to cool the gas or how to heat the gas. And finally, the beast of these models, which are the feedback from the stars and the feedback from the black holes. This is just in general. And here were some of the choices in the Illustris model. As you can imagine, a model like this necessarily entails many choices and free parameters, even though the general functioning is inspired either by things more as seen on observations or theoretical models which are tailored to study individual aspects of this chart. But I think that having many choices and free parameters in our type of models is not an issue as long as it's clear what kind of exercise we are doing. And I want to walk you through this. And again, many words, maybe follow my lead. So this is what we're trying to do. We are after a theory for galaxy physics, which is an effective theory. We cannot solve ab initio every possible physics mechanism which is underlying the physics of galaxies. And we actually want to form galaxies in a model that function in a widest possible range of masses and redshifts and times, evolutionary states, and so on and so forth. And in fact, because we just don't want to form galaxies, but we also want to take into account the effects of the hierarchical growth of structure. This is why we do cosmological simulations for galaxy physics, and this is why we do galaxies not in isolation. And once we have a model, an effective model that gets the average galaxy population, we are happy, and we use this simulation to understand how come, say, if you have a halo mass, how come that sometimes it hosts a galaxy of 5 × 10^11, another time 2 × 10^12 solar masses, and so on and so forth. So why there are disks and why there are spirals, and so on and so forth. Now, to choose our model and to calibrate it to get the average galaxy population, we need indeed to use some observational constraints. There are not many, actually, if you think about it. Oftentimes, they are, as I mentioned, the star formation rate density as a function of time of the whole whole universe, or the galaxy stellar mass function at redshift 0. But the idea is that once you get the average population by, let's say, tuning to some properties, everything else, I would say, is a prediction of the model, or it's a gift of the model, or something that can be at least used to check whether the model makes any sense or not. And this is the framework in which we are working in our business. And now I want to show you a few examples of predictions or gifts or applications of this type of simulations. And I'm using Illustris. For example, you still need thousands and thousands of galaxies to validate quenching theories. Maybe quenching theories that were suggested by data, like SDSS. This is a plot from SDSS, and this is the analog plot in the Illustris simulation, where you can see that if you take star-forming galaxy, the star formation rates don't depend on the density of their surroundings, but rather just depends on the galaxy mass. Again, you need hundreds of satellite galaxies residing in big objects to understand how satellites seize their star formation, quench, when they are part of a bigger object. This is the time for quenching as a function of stellar mass of objects in Illustris, and these are averages in Illustris, in big objects, 10 to the 14 solar mass clusters, and these are SDSS data again. You can see from our type of simulations that galaxies need various different times to quench according to their mass, according to the host in which they are sitting, and yet when you find an average, you can have gigantic dispersions. At fixed host satellite mass, at fixed host mass, you can get many different quenching time, very large differences. With simulations like Illustris, you can actually go with chirurgical precision and measure how many mergers galaxies have. So this is for mergers like these ones that maybe you cannot see very well, but they actually are very similar to what we see in nature. So in fact, you can plot the merger rate as a function of stellar mass of your galaxy, as a function of different type of merger ratios, as a function of time, and you can even count down that, yes, at redshift 0, more massy galaxies tend to have more major mergers than their low mass companions. And this also can be taken out from this kind of simulations. The mergers are really important because actually they are the reasons for which there are stellar halos. This is a topic very dear to my heart. Stellar halos are these low surface brightness envelopes of stellar mass surrounding galaxies. These are many from Illustris, and these are hundreds of kiloparsec, the galaxies in the very middle. This kind of simulation reproduces the stellar halo and the variety of them. For example, if you go and just measure the density profile in spherical symmetry, you can see that larger halo have shallower stellar halo than their low mass companions. And actually, with the simulation, we can actually see why there is a dispersion again here in this kind of scaling relation. Okay, obviously not all the stellar halos are smooth or spherical. Actually, some of them show some cool features. If you're interested in the features, you can also go and look for them in our simulation. These are observations of galaxies with shells, and these are analog from Illustris. And we have gone on and measured how many shells you expect around galaxies at redshift 0 of a given mass. So 20% more or less of galaxies at redshift 0 should have these features at many hundreds of kiloparsec away from their center, and these are actually signs of mergers. All right, I skipped that. So, of course, these are all kind of applications you can use the simulation for, but the simulation is not perfect. And this was actually pointed out from the very beginning. This is a series of limitation of Illustris that came out as soon as my colleague and myself started to compare the galaxy population to some statistics. Again, a very crowded plot. I think I would like you to focus on 3 things if you follow my lead. This is the galaxy stellar mass function, as a function of stellar mass, galaxy stellar mass, at redshift 0. And these are observational data, and the solid curve is Illustris. As you can see, there was an overproduction of small galaxies and massive galaxies at their both high and low mass end. Another aspect we will come back later is that Illustris galaxy did not show the right color by modality, or the color by modality that is there in SDSS. This is true in some particular galaxy stellar masses, where, well, actually the simulations are here and the data is over there. But maybe one of the most problematic issues with Illustris was that if you plot the mass in gas in your halos as a function of halo mass, it turned out that galaxies, the massive halos in Illustris were completely depleted of gas, or almost completely depleted. And this was immediately attributed to the way we were doing the AGN feedback in this simulation. So this kind of problems in the galaxy population cooked up in Illustris were the reasons for which we wanted to go farther and possibly try to solve them all. And this asked for making up and cooking up a new TNG model. So the TNG model is just this series of galaxy physics prescriptions which are behind our simulation. Let's see, it's always based on a repo. We use the similar framework of Illustris, always cosmological initial conditions. There were a series of numerical improvements implemented to a repo that we put together in the new TNG framework. But if you want to remember 3 things that make TNG different than Illustris is it includes magnetic fields, it includes magnetohydrodynamics. There is a new black hole-driven wind as a new type of feedback when the black holes are accreting low, and we have refined the galactic wind feedback. On top of it, now Arepo, for example, has a very cool shock finder, so we can actually trace shocks in the gas. We can follow the production of all metals by supernova type 1a, type 2 AGB stars separately, so we know who came from whom. And we also put a subgrid model for neutron star merger as a possible way to make Europium or a possible R-process phenomenon. But today I will focus on 2 aspects of the new model, which are the 2 feedback. And I will start with the galactic winds. Okay. The galactic winds is our way of implementing feedback from stars, feedback from supernova. So we have supernova that explodes and they release material and energy. We don't have the resolution to possibly follow the blast wave of the supernova. So we do something completely different, but yet that makes what we want. So what we do is that whenever we have a disk of a galaxy, this is seen in the cell, in the grid structure, there will be gas cells which are star forming. And what we need to do is we need to have a mechanism that moves around a bit the gas from star-forming regions to avoid to make too many stars. So this is the idea of the feedback, okay? And what we do, we simply bring some mass in the gas cells and we move it away. We make them wind particles and we push them away from the star-forming region. As you can imagine, whenever you do this, you have many choices to take. You have to decide how much mass you take away and you put into winds. You have to decide with velocity, which direction to give to the velocity, and so on and so forth. And to make the story short, in Illustris and TNG, we just took different choices on how we decided to do this wind. The problems I listed before, and again, this is only for people that know what we are talking about. The point is that the problems I mentioned before were all related to the fact that our galactic winds were too weak to avoid star formation in low-mass galaxies. And what we ended up doing with TNG was to make our wind faster across time, across masses, changing slightly their mass loading, and actually tying it to the properties of the interstellar medium. Now, I can see that this might look like a little ad hoc, but to be honest, we want this feedback to do what we want them to do, which is moving around the gas. So if I show you galaxies at redshift 2, and this is the gas density with these fields, the fields are the velocity fields of the gas, however crude our implementation is, it produces what we need. It produces outflows coming out from the galaxies. And this is either wherever, even if we do the TNG model, or if we do the same exact galaxies with the old model. In both cases, you have wonderfully fully regular galactic fountains, and in other cases, you just have a mess. But what I want to say is that the connection, what I described in the first slide, is something we implement in the very innermost regions of the galaxies to get something that can maybe be proved by observation and many kiloparsec away from the center of the galaxy. And the connection between the two is not obvious at all, but needs to be. You need to make a galaxy to see this connection. Now, talking about AGN feedback, you know, again, we don't know how supermassive black hole forms. So in our simulations, we seed black holes with particles which are allowed to grow in time. And then they exert some feedback. All this is done based on other theoretical models. So for example, we allow the black hole to grow in some fashion, like the Bondi-Hoyle formula for the accretion into the black holes, and so on and so forth. What really distinguishes Illustris from TNG is how we implemented one aspect of the black hole feedback. As I said, the black hole feedback is return of energy, possibly mass, or possibly momentum from the black hole to the surrounding gas. In Illustris, we were doing two types of modes. When the black hole is accreting fast, you do a thermal dump in the surrounding of your quasar. This is called quasar mode. When the black hole was not accreting very fast, there would have been the so-called thermal bubbles, which I describe in a second. In TNG, we have changed the thermal bubble. We don't touch the quasar mode, but we have changed quite significantly what we do at low accretion states, which are, okay, maybe it's not the best picture of it, but the thermal bubbles were like this. The black hole is accreting slow. From time to time, it deposits thermal energy, but it did it even possibly very far away from the center, in the intercluster medium. The idea was to mimic the cavities which are seen in the intercluster medium of massive objects. Now, in TNG, we do something very different. We kick around the gas from the surrounding of the black hole. So this is effectively a kinetic feedback. And again, it might seem artificial, but this feedback, they do what they are supposed to do, which is moving around the gas and possibly heat it up. I'll show this here in this movie of mass-weighted gas temperature of a quite large, but not too large, halo in the Illustris model and in the TNG model. You go from black to red, from cold to hot, and these are two identical. They are the identical cosmological zoom simulations of this cluster. And as you can see, they are behaving quite different. Two different AGN feedback, two different behavior. And still a certain field of gas in the halo, like this. I show you the outcome of the same experiment on a smaller halo, 10 to the 13. This was with Illustris, and this was TNG. With Illustris, there was so little gas, we couldn't even do a map of the temperature, essentially. Okay. So, as I said, MHD, different galactic winds, and a new kinetic black hole-driven wind. Let's see how the galaxies look like with these changes. Thanks God, the galaxies still look like galaxies. And I show them here, just qualitatively, just to say that you still get, from our simulation, wonderfully thin disks, not so thin, but, you know, disks and elliptical galaxies. More quantitatively, I can show you 6 quantities that we actually use to decide how to change the model in practice. Again, a complicated plot, but follow me. We have star formation rate density as a function of redshift, the stellar mass divided by halo mass as a function of halo mass, the galaxy stellar mass function at redshift 0, the black hole mass galaxy mass relation, the fraction of gas in the halo as a function of halo, and the sizes of galaxies, stellar mass size, the stellar size versus stellar mass. And in all panels, you see in red the implementation with the Illustris model, the old one, and in black, the new one. And what I want you to notice is that we managed, maybe, to change some aspects that we really wanted to change. I told you before, if I see my pointer here, that the galaxy stellar mass function was too high, and we managed to go down. Also, the efficiency of making stars in low mass halo, we needed to be lower, and it went down, and so on and so forth. At the high mass end, all the changes are possibly due to the change in the AGN feedback, and for example, we managed to get a larger gas fraction in the massive halos. This is 10 to the 13. Here there will be 10 to the 14, which is at least more similar to what obtained in observations. Yeah, thank you. So, but for the star formation rate density, the color lines are all running averages from the simulation. Actually, the tiny dots are individual dots from the TNG model, but every other gray, and we should change this, every other gray is actually some observational constraints of reference. However, at this stage of the modeling, we didn't do real mock observations of our galaxies. So we used, say, the galaxy stellar mass function constraints as a, as a guideline, but we didn't want to fit it perfectly because we would have not been doing the right thing in any case. All right. Now, so far, I just talked about the center body of galaxies, particularly the stellar mass. Here, I want to show you what happens outside the galaxies. In the upper panel, you see, in all these plots, you see 10 megaparsec cubes in gas density, gas temperature, gas metallicity, and stellar density. And in the top panel, you see this box in Illustris, in the Illustris model, and in the bottom, in the TNG model. We are about a redshift 3. You cannot see it here, but it's running. You see the structures are forming or collapsing. And what I would like you to notice is what happens on large scales. Here, there are the halos, which are assembling. In the middle of those, there are the galaxies, whose statistical quantities I've shown you before. But what I wanted to show is that on the larger scales, the two models can give differences that are much more dramatic than on the galaxy level. In fact, if you can see here, this is the old AGN feedback model driving these bubbles, which in turn produce the enrichment of the IGM. So what I want to say with this movie is the following. Well, first of all, that when we say that we are dealing with a very multi-physics, multi-scale problem is actually true. A model can give the same exact Milky Way-like galaxies and yet produce a completely different enrichment of the intergalactic medium. And the second thing is that at the end of the day, if you want to validate your model, even if you want just to do galaxies, you have to make galaxies in the full cosmological context, in the large-scale structure, and so on and so forth, because you can get constraining power also in the large-scale structure. And this is why we also like to make large cosmological volumes. We want to have thousands of galaxies, and we want to have them embedded in the large-scale structure, which is motivated by cosmological initial conditions. Just to draw your attention, it's gone. There were gaseous halo and non-gaseous halos in the two cases. Very well. This brought me to introducing you to the new simulation. This is the family picture of the TNG simulations. There are 3 volumes of 100, 300, and 50 megaparsec on a side, respectively. They all have been running with the same model invariant across runs, with updated cosmology to Planck. They all include MHD, but they are at different resolutions. In fact, we run every simulation at different resolutions, but the flagship, the coolest one, is the highest is here, followed by TNG 100, followed by TNG 300. In fact, our new flagship box called TNG 100 shared the same exact initial conditions of Illustris, but for the changes in cosmology, and the same resolution. So now we can really do halo by halo, galaxy by galaxy comparisons. We have made all these simulations in Stuttgart on a machine called Hazelhen, and apologies. And TNG 100 and TNG 300 are actually completed. TNG 50 may be completed in a few months. But today, therefore, I will be talking about mostly TNG 100 and TNG 300. I said they have different resolution. I will need a whole seminar to describe the resolution of these simulations. I will not do that. But if you want to remember two numbers, In TNG 100, a stellar particle is something like 10 to the 6 solar masses. In TNG 300, which is the gigantic volume, is still 10 to the 7 solar masses. The dark matter particle is of the order of 8 10 to the 6 solar masses in TNG 100, and of the order of 6 10 to the 7 in the gigantic volume. Different resolutions, different scopes. In fact, if you go and ask, okay, what objects can I study with these simulations? Well, you can do quite a few things, but the strength of the big box, which is identified here in the TNG 300 boost, is that if in the TNG 100 volume you have something like 10 halos, like clusters, 10 to the 14 solar masses and above, you start to get 300 objects in TNG 300, actually, above 10 to the 14 solar masses, and so on and so forth. But perhaps a nice way to convince you of the possibilities with this kind of simulations of what you can do is just to show you how the simulation look like. And in the next slides, I'm just going through pictures of the TNG 100 box. So here, the span of the screen is 100 megaparsec, more or less. And here you see all our halos in this new simulation. This is dark matter density. Now it's gas density. This is the velocity of the gas field. This is the temperature of the gas, where you can see the temperature is very high in the middle of your halo. It goes low in the voids and stuff like this. Oh, you wanted the color codes. You wanted the color bars. No, there's no color bar. Dark matter density, sorry. I didn't put the color bars. So I say you go to more than 10 to the 8, 10 to the 9 Kelvin in the middle. Yeah, sorry about that. Good point. This is how the box would look like if you were looking at it in X-ray, actually bolometric, with X-ray halos in the most massive objects. And here is the metallicity of the gas, where you have actually polluted very highly the highly clustered regions, but not very much the voids. And I told you we can follow the metallicity produced by different type of things. This is, for example, the ratio of the metallicity of the gas produced by supernova type 1a divided by supernova type 2. Okay, I don't know what you're going to learn from it, but we can do that. It's just to tease you. And this is, for example, the magnetic field intensity, where you can see that in our type of simulation, you can actually get consistently amplified magnetic fields in high density halos. 10 to the minus 14 Gauss co-moving and at redshift 130. Okay, and then I told you that we actually can follow shocks. So this is actually, these are the Mach number of the shocks happening in our boxes. You can actually see the collapse even along the filaments of the structures. And finally, even more so, you can see the shocks in the energy dissipated in the shocks. If I was to zoom in, you could both see shocks and energy dissipated because of the gravitational collapse, as well as because of the feedback mechanisms. And I go back to the prosaic stars, which are actually the reason for which we all started to do these kind of simulations. And I show the stars because they are what I'm going to talk about as applications, but we should never forget that all the link behind stars and their matter is, of course, the gas, which is why I indulge quite a bit on the gas part. Applications. I have a few minutes, and I want to go through a series of applications that we can do from TNG. Oh. He wants to stop as well. No. Okay. And I will focus now on the galaxy colors, and magnetic fields. So I show you the galaxies in the new model seem to make sense, at least from a statistical viewpoint. If you look inside the galaxies, they actually look like galaxies. On the left, even more so, on the left there are galaxies which have red colors, and on the right, which have blue colors. But we can do actually much better, and we can compare the TNG galaxy color by modality to SDSS. This is what we do here. This is a paper to be submitted by my colleague Dylan Nelson. SDSS is in black. The Illustris and the TNG results are in red and blue, respectively. Here you see G minus R. Different panels are different galaxy stellar masses. And in this plot, we actually did a very careful mock observation of our simulated galaxy to try at least to possibly take into account effects of dust and reddening. And what I wanted to show is that if in Illustris there were some bins in galaxy mass where we had no red galaxies, we recovered them compared to SDSS, which is good. We can also go to the simulation and ask to every galaxy, how did you move through the color stellar mass diagram? And we can draw charts, or we can actually do more quantitative plots, which are there, but this is good for a colloquium. So here is color galaxy stellar mass. These clouds are the loci of the blue clouds and the red sequence, and all the different types of ways galaxy can go from blue to red. And some galaxy can go to red via the green valley. They can go to the green valley, then grow a lot while they are in the red sequence, and so on and so forth. All topics which people are interested on their own. One aspect I would like to show you actually is that we can see features we would have never imagined. If I plot again, well, Dylan plots again color versus stellar mass, and this is again blue, cloud, red sequence. And if you plot in every pixel the average magnetic field intensity in the interstellar medium and CGM of these galaxies, this is what you get. In practice, you get a prediction. The blue galaxies have much larger magnetic fields than red galaxies. And I'm not saying that there is a causation. It's just a correlation among things I'm happy to discuss about. Similarly, in fact, if you plot the stellar gas density and magnetic intensity of these galaxies versus elliptical, both the gas field velocity as well as the B field, magnetic field patterns are very different. So you have very ordered B fields in the disks, while the field orientation becomes a disaster in elliptical galaxies, exactly like the gas. This is for small mass galaxies. I have an interest in very massive objects. And in fact, I told you, in TNG 300, we have hundreds of galaxies residing in halos more massive than 10 to the 14. These are just examples of them. So our type of simulations, when we say in the full cosmological context, they reproduce massive halos. These you cannot see. These are hundreds of kiloparsecs. And this is a 10 to the 15 cluster of galaxy. This is a 5, 4, 10 to the 14 cluster of galaxies. So you recover groups and cluster of galaxies as observed, dominated by a central galaxy with a family of more or less luminous satellites, and all amid low surface brightness stars. Low surface brightness stellar mass, meaning all this diffuse light, which is called intracluster light or stellar halo. And we can use our simulation to provide measurements of the stellar mass budget in these halos from models, finally at these very large masses. This is what we have seen before, is the stellar to halo mass relation as a function of halo mass. And the gray are semi-empirical or observationally inferred constraints on this. What you can see is what we always have seen, that 10 to the 12 Milky Way-like halos are the most efficient in making stars. And then we go down at the low masses, and then we go down also at the high masses. There's a big debate on how steep you should fall. But in fact, for these massive objects, it really matters what you call galaxy. If I look at the galaxy cluster, this is a whole halo of 10 to the 14 solar mass, say. The central galaxy is somewhere here. There are all the satellite galaxies, but the central galaxy has no boundary. In fact, there is all this diffuse light, as I said. So this relation changes quite a bit according to when you stop calling these stars part to the central galaxy or part to the outskirts of the intercluster light. And so, in fact, you can change this relation from here to there if you account subsequently for the mass, say, in 30 kiloparsec, or the mass, diffuse mass, stellar mass across the whole halo, or if you also add satellite galaxies. And we can now really measure 10 to the 15 solar mass objects can have 10 times more stellar mass beyond 30 kiloparsec than inside 30 kiloparsec. This is just to give an idea of how much is around, how much stars. And we know why, because these objects form at the end of the universe history, and they form by smashing together many galaxies giga-years after giga-years. So this is a movie by my colleague where you see indeed the assembly of an elliptical galaxy. As you can see, there are many units which will make the final galaxy a ratio 0 if we stop rotating and showing you all the possible projections. In fact, in the simulations we can go and measure for every star who made the star, whether the central galaxy across its lifetime or whether the stars came from incoming satellites, got stripped, and produced and left their stars to the more massive one. These are called ex situ or accreted stars, and this is one of the last plots I want to show, is the mass in the ex situ accreted component as a function of halo mass. So in practice, if you look at very massive objects, here, the mass of the very massive objects is for more than 50% have been accreted, has not been made by their star formation. And again, this is something that we can simply quantify and measure, and we can then see effects in the stellar population, in the age gradients, in the metallicities, and so on and so forth. If I may take another 5 minutes, I will then overwhelm you a little further with another type of applications of these simulations, which is wider in scope, which is, well, can we use this simulation to actually learn something about cosmology? And I would say that the answer is yes, because we know since many years that the galaxies and the physics of galaxies alter what we know about the distribution of dark matter. I show this just qualitatively for a series of studies I've done in the past, many works. I've tried to assess this. I'm using here a Milky Way-like simulated galaxy. It's Eris, and I just want to show that if I do the same simulation in the full physics model or in the dark matter-only model, I can get quite different things. For example, this is the density profile of the halos, and the solid black is dark matter profile in the dark matter-only simulation, and in dashed is the dark matter profile in the full physics galaxy. As you can see, they're quite different. If I plot the shapes of the dark matter density fields, they're very different. We know since a while that the presence of a galaxy tends to make halos more spherical. We also know that, for example, if you put a galaxy in the middle of your halo, your satellites might have a different chance to survive the tidal fields. So you can also affect the sub-halo mass function, which in turn affects our capability of making any claim about the number of satellites in the Milky Way. And finally, if you want to do direct dark matter searches and you are looking for signals that depend on the velocity field of the dark matter at the sun, you may want to extend the models you are using from the dark matter only prediction to maybe full physics predictions. This is just to give you some examples. In our type of simulations, we see something even more fundamental. Is the definition of a mass, halo mass itself, kind of changes. You can see this here. For the same objects, as a function of halo mass, you can plot the mass that you would label the object with in the full physics run or in the dark matter only run. And you can get different things by also 20-30%. This, in turn, affects predictions from simulation, from embody, for the dark matter halo mass function. And if you're using a dark matter halo mass function to constrain sigma 8 and omega m, you might get very different results. For example, are the constraints of sigma 8 of omega m that you obtain if you do an experiment where you inputted an abundance of clusters seen in X-ray here, and you study and you fit your data with a hydro model or with a dark matter-only model. Quite different. So we need to be careful when we are trying to do precision cosmology. The problem, of course, is that not everybody agrees on the amount nor on the way we change these quantities. For example, this is the results from the Eagle simulation. So there's quite a lot to do still in this business. The change of mass is just a reflection of the fact that we change the profiles. This is our mass enclosed. The circular velocity profile as a function of radius in different simulation. A dark matter-only prediction, TNG and Illustris. Very different. Some are much more contracted than others, and so on and so forth. And all this is because, in fact, we are changing the correlation functions of the material behind. I can show you this here from a paper from Volker and Rudiger to be coming out soon. And this is just what they did is just go into our simulations and check what is the correlation functions or the power spectrum of the smooth material, where smooth material is the total, the gas, the dark matter, the stars, and the black holes. For example, this is a power spectrum. You can see the linear prediction. You can see how we expected that when you are not in linear regime, you have a lot of power in the low masses, in the low scales. These are small scales. But in fact, different types of materials cluster quite differently. Particularly the stars are very cool. They are always much, much more clustered, yes, than everything else. And this has to do with the way they form and where they are located inside the halos. But in fact, if you go even farther and you do the ratio between the power spectrum of your matter predicted by a full physics simulation to the one predicted by a dark matter-only simulation, you can get quite some different answers. In blue was the old Illustris simulation. In green and in red are Eagle and TNG 100. And this band is showing you the type of accuracy people want, the 1% accuracy in the power spectrum people want to do dark energy surveys with. I'm just saying that we have to work pretty hard to make sure that we know how to fit our data with in this business. So I conclude here, and I hope I demonstrated that cosmological simulations are getting more and more interesting. The levels of realism and complexity is growing, but in a good manner. I think we can use them to predict new aspects that we didn't know, or also to refine things we knew already, but not quantitatively. In particularly, I introduced IllustrisTNG. If you want to remember 3 things about IllustrisTNG, what it does, it solves essentially all the problems of Illustris. Well, it was tailored to do that. It has new physics, a new black hole-driven wind model by Hitz, People, Reiner, and Volker, and it expands a lot upon the scope of what can be reached with these kind of simulations. And I've also shown you that we can use them to make sure we derive cosmological related statements in a real accurate manner, although I also show you that there is still quite some uncertainties in this kind of prediction, and therefore we need to study more. So I thank you very much. I leave you this movie.
So thank you, Annalisa, for this fantastic overview of what you can do now with galaxy formation simulations and what are the achievements and still the open issues that are around in abundance. There are, I'm sure, many questions. Who would like to start? Andreas. Wait.
On the left, yeah. on the left plot, what is the main reason that you get this bump at a few kiloparsec? Is it a more massive bulge or is it a more compact bulge?
Yeah. So these are all galaxies in a 10 to the 12 mass beam. And in fact, I mean, we always had this problem in numerical simulations that we were overdoing bulges in the middle. In Illustris, we were underdoing them. In fact, we had in Illustris, the Milky Way-like galaxies might have a good disk, but they rarely exhibit a bump of 250 kilometers a second, and now we just get some get a bump, and these are bulges in practice.
So are they more massive or more compact, your bulges?
They are, they could be both. It could be both. We do definitely see that the sizes are smaller, but we never did a decomposition, so I cannot answer precisely.
Can I ask a number of details about the magnetic fields? The first is, what is the structure of the initial magnetic field configuration?
Yes.
And the second is, does the star formation recipe you have depend on the magnetic fields? And the third would be, do you have a significant amount of magnetic pressure?
Yeah, okay. So at the initial conditions, where we have them at about 130 in redshift, the seed magnetic field is a uniform field in one direction, whatever that is the z direction of our box. And in fact, when the magnetic field doesn't get amplified, in the very, very, very low density voids, we can still see the initial field. However, inside the higher density regions, it's perfectly, it's amplified and it has all the different type of topologies. Whether we change the star formation recipe for doing, it depends on the field. So the short answer is no, but we can do very different things. So when we do star formation, in practice, we just take away a piece of a gas cells and we make it a star. So we take some mass of gas cells or all the gas cells and we make to be a star. And we have changed many recipes whether whether the magnetic fields could have been put into the stars, and therefore we would have moved the same amount of the analog amount of magnetic field from the gas cells or not. In the end, in IllustrisTNG, sorry, but we changed like 1,000 of times. Rudiger, I need your help here. In the end, I think what we do is that whenever we make a star, we just make the analog magnetic fields of the gas mass that goes into stars vanish. Yeah. And then the magnetic pressure. So again, the quantitative answer depends very much on where you look at. Generally speaking, what we say is that the magnetic fields are never dynamically important, in the sense that the magnetic pressure is, generally speaking, smaller than a turbulent pressure, kinetic pressure of the gas. However, this depends very much on where you look at. For example, in these galaxies, there are regimes in the profile where actually the magnetic pressure may become not tiny, not small. Yes. Yes.
So, next question.
Excellent talk, Annalisa, and very interesting results. Congrats. So I was a bit intrigued by your baryon fraction plot, where you were looking at the high mass end and basically did the accounting exercise for, okay, how do you actually define your massive halos?
Yeah.
Yes, this one indeed. So, of course, the classical story is you need AGN feedback here at the high mass end, and I imagine the AGN feedback is particularly important when you're looking at the stellar spheroids on sort of sub 30 kiloparsec scales. Do you actually still need AGN feedback if you include the ICL and the satellites? Because I'm imagining you're basically just picking stuff from the left-hand side of the mass range and putting it on the right-hand side.
I thought that we solved everything for no reason. Yes?
Yeah.
No, actually no. The answer is no, because still you may have, when I say that even within 30 kiloparsec, or even let's say the in situ stars, this is what the black hole feedback have a chance to affect the production of. We say they are 10%, 20% of the total within 30 kiloparsec. They wouldn't be 20% of the total if our AGN feedback was terrible. So the answer is we still need it. And indeed, yes, so I think the right, we still need to compare in small apertures if we want to assess the needs for the black hole feedback. Yeah.
But you can just do the same exercise for Illustris, right? Because there you have a different
yes,
AGN model.
I didn't show this here. In Illustris, okay, to be honest, so we are indeed, our AGN feedback was less effective at reducing star formation, but this was true in a very specific point, which was here, 10 to the 13, 10 to the 14 solar masses, yeah? And indeed then it goes a bit, yeah, but I cannot assess the 10 to the 15 because I don't have the Illustris model in these large volumes, but yes, you got the point.
So Pascal?
All right, great talk. I was with you all the way till you showed the plot of baryons and dark matter, and I'll tell you why. So I see the immense progress you've made between Illustris and IllustrisTNG by changing the feedback process mostly, right? But you agree that if a feedback process gives you the right answer, doesn't mean it's the correct feedback process.
This is true.
Right. So does it make sense then to try and ask the question of how are the baryons related to dark matter when we don't really understand what is the acting agent on the baryons and how it acts in the first place to actually relate it to the beginning?
Yes, thanks for asking. Well, my approach is the following. If I want to assess the effects of baryons on dark matter, I would like to start from baryons whose distribution, phase space properties and stuff are as close as possible to the reality. It might be, indeed what we see is that different models producing the same galaxies but having very different gas fraction produce very different effects of baryons on the dark matter. In the end, it all depends on what the gas does. But my approach is that I want to start at least with a model that makes galaxies that seem like galaxies. And then we start to, you know, work better and better to refine this. Absolutely. In fact, you want to use this type of simulation to understand what causes these effects of baryons, and then we can go back and see whether these causes are plausible.
So Daniel Severino?
I have one question about the wind recipe. So it seems TNG needs to inject more energy in low mass halos and high low metallicity. So what's the physics behind that recipe? Any thoughts,
Yes.
any ideas?
See, so that's what we did. We indeed put a mass loading factor that depends on the metallicity of the ICM. And the idea is that, in practice, what we don't change the energy released by supernova, but what we change is how we think this energy should be coupled to the ISM. And we can also imagine that there are more larger radiative losses there where there are different metallicities in the ISM. In larger galaxies with larger metallicities.
So before I come to the other side, one more question here, and then I come to Hans Walter and Richard.
Thanks. So I'm still a bit puzzled by this plot. Isn't the ambiguity resolved by counting the dark matter in the same way as you count the stars, in the following sense that well, obviously some of the dark matter particles that are part of the halo now have come from mergers. They have been brought in at a certain time. So, and I guess these are being counted, right? Because these are part of the total halo mass. So why not also count the stars that have been brought in at later times?
I agree. So in fact, first of all, I would say the same. We should count the stars as we count the halos. So what I'm saying is that if I'm talking about a plot which is about the star formation efficiency, yes, either we just talk about the in situ stars, or I want to talk about all the stars within a halo. And I agree with that. What I advocate here is that the only alternative to make quantitative comparison is to just specify the apertures over which you're measuring your mass. And then we are good. But I agree completely. So in fact, my favorite line should become solid is this one, is everything.
Annalisa, I wanted to ask you about your basically last graph you showed that showed the large-scale structure measurements that exactly that on the right-hand panel, right? The reason why this matters is because people are worried that for Euclid or something else, even if you measure large-scale structure infinitely precise, you can't interpret it in terms of cosmology. Now, does it actually matter that those lines are close to the zero line that you have there, or is it comforting enough that as of now, Eagle, TNG are very close to one another, so there's something correctable, presuming that that's for good physical, not sociological reasons?
It's not the sociological fact, the fact that we end up on Eagle, because it's still for the wrong reasons. We have completely different gas fractions, so just even to go back to one of the questions. What I would say is just that we could use these alternative models to place systematic error bars on our constraints. This is and it's true, they are not so far from zero anymore. And we know Illustris was bad because it had no gas in the halos, but at this point I cannot distinguish between one or the other. I cannot put a prior on my favorite model at the moment for which we could do the fit for dark energy service. So what I would say is that let's just put a systematic error bars which also take into account the underlying theoretical uncertainty. This is what I would suggest.
Yeah, hi, thank you very much. Just one of your results was quantifying, predicting the stellar content of the large-scale dark matter halos in groups and clusters. Presumably those stars will be injecting metals into the intergalactic medium. So my question is, how important is that process compared to other processes such as galactic winds or sort of impulsive dispersion of gas in mergers?
So let me try to understand. So
I mean, we've got a post-main sequence evolution of the stars freely moving around the halo. They're going to be injecting metals. How important is that?
We cannot address this at all. I'm sorry. We cannot do this. So in that sense, we do inject metals when stars are going off like supernova. And we also do inject metals from AGB stars. But we do it only on a quantitative manner. We don't do it in a specially resolved manner, if you know what I mean. But the point is that, so I would still think that the pollution of the stellar halos and of the intercluster light is just due to whatever we do in the gas is not coming from the individual stars in the stellar halo, because in the Milky Way, the stellar halo stars are still a few %, while you have all your gas CGM, which is coming from below, from the feedback, from inside. So to be honest, I think I would guess it's a negligible contribution of the pollution from diffuse stars to the gas metallicity, if I got your question right.
So earlier in the talk, you had a plot of the gas fraction versus stellar mass, and you had very big differences at the low mass end between Illustris and IllustrisTNG.
Yeah.
So I'm trying to understand why this is. Is it because your stellar feedback is roughly the same, right? Your star formation feedback?
It is.
So yeah, that plot in the bottom middle.
It's conceptually the same, but it's not. Sorry.
You actually labeled it interesting, I think, in your...
I have interesting. So
I'm curious what chart.
So this we know. Okay. So what happens here is the different AGM feedback. What happens here is mostly due to the galactic winds, as you say. We didn't change the qualitative aspects of the galactic winds, but quantitatively, yes, because we now we put a minimum floor to the velocity of the winds in galaxies. So galaxies at the high mass end, at the low mass end, have always a floor. So if you eject winds from small galaxies, it's always at least a given amount, which is 350 kilometers a second. And this actually makes the gas less prone to be able to come back.
But there are many observational constraints, right? All those small points are from the models you said, and so alfalfa has many constraints.
I would say that the constraints are really shaky, and this is why I want people to go and see this, even for the Milky Way, which is here. Honestly, if you think about cos-halo and cos-dwarf, whatever, we have to go from gas fraction to whatever they measure, some oxygen 6 or whatever, nitrogen 4, column densities and stuff, and then we can say. But even so, I didn't show you, but the points should give you an idea of the dispersion. It's still gigantic. So we really need, yes, please, go and measure the CGM. Yes, this is true. But I don't think there are so many for just the amount of gas in the halo.
So we slowly need to come to an end. Second to last question.
It's just a short one with regards to one of your very last plots, the one with the power spectra.
Yeah.
If you could go to this one again, maybe.
See? One second. My computer is giving up. Okay, arriving.
Yes. We already talked about the scatter between simulations, but now just within Illustris or IllustrisTNG on the left-hand side, I found impressively high Fourier modes up to which this is plotted. It's like 10 to the 2, 10 to the 3. Just wondering what is the level of confidence within the simulation for the value of the power spectra at these large K values.
Just 1 second. So this is only TNT. Say the full physics, the full material is the black, which is also very close to the dark matter only. And I would say that until we hit the very nonlinear regime, we are good. These are, there's no, I'm pretty sure, these are cosmologically motivated power spectra. So this is perfectly on top of a Planck expected linear power spectrum. At the nonlinear regimes, to be honest, it's actually very difficult to say how we are doing here. What plots what data points shall I plot there? Here? All the people doing halo models are struggling at indeed forecasting how nonlinear the nonlinearities are at the large case, in the small case. Yeah. Yeah.
So pretty hard within the simulation to give a level of confidence for the very high nonlinear.
I think it's the best we can do. Are you guessing? Are you asking whether if we have ways to assess whether we are doing the nonlinearities badly? Oh boy, sorry, no, completely different question. I don't know. We should put it.
Yes.
We should put the yellow bars. Yeah.
So let me take the liberty and ask the very last question. I'm particularly intrigued by the fact that you find much less efficient metal mixing into the void regions. And so I was wondering, working on first star formation, how much volume you get at what redshift that is still completely pristine, and what star formation you may get there. But you may have a resolution issue also in these regions.
So this is depicted in this kind of, so we have not done more than the movie.
Okay.
So this is the short answer. Sorry. But indeed, I think pollution of the IgM and low density is very constraining.
Yes, I think it would be very interesting to look at that problem.
So we have a couple of projects going into that direction, and even just to compare, well, we always do comparison between Illustris and TNG now, so we can discriminate between the effects of the AGM feedback on these large scales. However, then when we start to say the pollution at very, very high redshifts, it depends on how much star formation we are doing at this very, very high redshift, and this is very model dependent at the moment. And TNG and Illustris are producing very different star formation rate density, say redshift 7 or 8. At the moment, we have no reason to say whether one or the other is better than the other.
Okay, I see.
So it's pure, we have to study that part more carefully.
Okay, I think that's a very good end. So with that, many thanks for this fantastic talk and the many discussions it has raised.